Let's look at some examples of groups and some known examples also. So let's recall what we have studied, the definition, and so recall the definition. So I will be just let G star be a anonymity set with an operation. Then we need 4 properties. First of all, star is a binary operation, or we can say operation is star is closed. Second thing is star is associative. A detailed description of what we are writing down is already given in the first lecture. Third one is identity, or E. Identity exists in the set G. Fourth one, for each element A in G, an element A inverse exists in G. Okay. So these are the 4 properties a group has to follow. Now we go for one by one. So first example is our motivating example, which is integers under addition. So here we can see that associativity is there. Also it is a binary operation. For any 2 integers you take, a plus b again going to be in integers. So that is there. Now 0 act as identity. If you add 0 to anything, you get back that number. Now for any h in Z, you can say minus h in Z, so that h plus minus h equal to 0, as well as minus h plus h also equal to 0. So it is a group. Second thing, similarly you can see that R under addition, that is real numbers under addition, rational numbers under addition, finally complex numbers under addition is also groups. Now we look at what happens if you use multiplication, usual multiplication in real numbers with some sets. So let's look at Q star under normal multiplication. So what is Q star means? It is non-zero rationals under the operation usual or ordinary multiplication. So you can see that the associativity is there, and if you take any AB in Q star, you can see that the product is also in Q star. Why? So what I am telling is the product is 0 only when one of them is 0, either A equal to 0 or B equal to 0. So you will not, because we have both are non-zero AB, you will not get the product is 0. That means the product is always a non-zero rational. So the closure property is there. Second thing, who is the identity? So 1 act as an identity in Q star, because if you multiply A with 1 you get A, similarly 1 with A. Now if A is not equal to 0, you can define the quantity 1 by A. and this is also in Q star, because 1 is an integer, a is also an integer. So 1 by a is a element in Q star. So if you put a multiplied by 1 by a, you get the identity back. Similarly, 1 by a times a also 1. So every condition is follows. So non-zero rationals under multiplication is a group. Similarly, I use this symbol for similarly. Similarly, you can see R star under multiplication is a group. Similarly, C star, complex numbers under usual multiplication is a group. So this multiplication is complex multiplication. You can check what is it. Complex multiplication. Okay, now let's move to something different types of sets. Like we can take the set of all matrices. So let Mn of R denotes all n by n matrices with real entries. I should write real entries. What do you mean by this? For example, we can talk about M2R. So these are all 2 by 2 matrices, right? So that each A, B, C, D is coming from the real numbers. That's the idea. And if you use addition, our operation is matrix addition. So what is matrix addition? You're adding component wise, right? So A, B, C, D plus some P, Q, R, S. We define the addition is simply A plus P, B plus Q, C plus R, and D plus S. So if you define multiplication like this becomes a group. Why? Because I write in a one step, because for A, B, C, D plus minus A, minus B, minus C, minus C, D, you get what is called a zero matrix. So this zero matrix is the identity, and this is inverse of any matrix of this form, right? So this one line defines whole thing. So what I can say is M n, you can generalize it to n by n matrix. MNR plus matrix addition, I call it is plus M, is a group. Okay. So one more interesting thing, can we define matrix multiplication? So you know what is a matrix multiplication, I think. So but to know matrix multiplication, so what is matrix multiplication? Let me define. So if two matrices are multiplied in this fashion, so multiplication is simply, it is AP plus BR. So you go this with this row with this column, and you finish it again, then you move to this column. So that is AQ plus BS. Then you move to second row, go for this column again, it is CP plus DR. Then you move to another column, it is CQ plus DS. You might have studied already in the first semester in linear algebra course. So this is a matrix multiplication, but you can't. So what is the problem with this? So if you multiply, so what is the identity? So identity matrix here, you can see if you multiply any matrix with this matrix I, you get A back. You can verify this if you want to. So this is true. So now we need for every A inverse. So you know that the formula of inverse is, you may have studied, it is adjoint A divided by determinant of A. So inverse exists only when the determinant of A is non-zero, right? So if it is non-zero, then A inverse exists. So such fellows is you can make like this. So you get for every A if determinant non-zero. So what you can observe is not every MNR is not a group. I will say why later in non examples is not a group. You think why it is? Because not every matrix has an inverse, but we define something GLNR, that is all matrices A in MNR, okay, it is a n-bind matrix, so that the determinant is non-zero. So if this happens, then GLNR under matrix multiplication is a group. Associativity you can try to prove it. Okay, so inverse exists, identity exists, binary operation. Okay, whether it is binary operation, that's the question. You take two matrices AB from GLNR. Am I sure that the product AB also GLNR? So what is the meaning? So I am questioning this. Is AB. So what do you mean by AB is in GLNR means you should prove that the product, the determinant has to be non-zero. So how do you prove this? So you have determinant of A is non-zero because that is in GLNR, B is non-zero, the same reason. Now assume if AB, so now you take, you must have a result, you can prove this later. Determinant of AB is equal to determinant of A times determinant of B. Okay, so this result shows you if AB is 0, this implies what? Determinant of A, determinant of B is 0. This means determinant of A equal to 0 or B equal to 0. But we have they are both non-zero. So that is a contradiction. So contradiction happened because you assume the cardinality of, I mean the determinant of AB is 0. So that is not a chance. So AB is, determinant of AB is non-zero, and that proves AB is inside GLNR. So this is a binary operation. So matrix multiplication is a binary operation on GLNR. Okay, so in all those cases binary operation is there, it is a binary operation and it inverse exists, identity exists, so it is a group. Okay, now we go for another kind of a set, which is you take a, so let X be a non-empty set. Now consider the power set of this. So power set is what? Subsets of X. So you want to define some operation on the power sets. So what I am going to define is, so let me define, so H and K are belongs to the power set. Okay, so they are in power set means they are subsets of X. So what I am going to define, I define an operation H symmetric difference. So we call it a symmetric difference. The idea is very simple. It is H union K minus H intersection K. The same thing we can written as H difference K union K difference H. Symmetric difference. Why it is called symmetric difference? Because of this. Because you are doing difference from H, Similarly, you are doing difference from k. So symmetrically you are taking difference. Okay, how this becomes a group? So let's look at the diagrammatic, the Venn diagrammatic representation of what this operation gives you. So suppose this is h and k, and what is h difference k here? What is k difference h here? So it is same as you taking the union and delete this h intersection k. Now what is the identity here? So if you make a symmetric difference with the phi is an empty set, right? What do you get? So you get we use the first form, so h union phi minus h intersection phi. So what you get is h union phi is what? H itself. If h intersection phi only. So if you take empty set from h, what do you get? H itself. So this is same as here also. So that means phi act as a identity. Phi is the identity. Now how do you get back identity? What is the inverse? So if you are given a h in power set of x, what is the inverse? So to get inverse, try h symmetric difference h itself. So what you get is h union h minus h intersection. H union h is what? H itself. H intersection h, h itself. What do you get? Phi. So the inverse of h inverse is h itself, right? So this is a particular kind of group. So if you make x, if you take x equal to natural numbers, then power set of n is a it is an infinite set where all element has its own inverse, because they are inverse of each other. I mean the same fellow is the inverse of itself. So this is a good example of that, all right. And we will quote this example in further classes for particular definitions, right. So what you can see is power set of x with this symmetric difference is a group. It's a group. So what I have, so you can, it's very clear the why binary operation is because whatever you do, this is again going to be a subset of x. So binary operation is not a deal. Binary operation works. How do you prove associativity? So you should take 3 subset of x, and you should prove that h symmetric difference k, symmetric difference f, it is equal to h symmetric difference k symmetric difference f. So maybe you can prove it using diagrams, and for example let's look at the left hand side how the diagram will come. So 3 sets you are taking, so h k f. So in the first operation h symmetric difference k, so what you are getting is this is what you get, right. Then what happens, you are taking symmetric difference with the f. So so what is symmetric difference with the f? It is let's see, let's take h and h, this is equal to some alpha. So what is alpha f? Is it is simply alpha union f minus alpha intersection f, right. So you can see what is alpha union f. So alpha union f is you can see this is the complete thing it will come, right. So in the second step what you get, so alpha union F I am going to draw. So this is, you can see everything will come like except the small portion. So this is alpha union F. Now what is alpha intersection F? So alpha intersection F you have to draw like that. So this is alpha intersection F, right? You can see from the first picture. Okay, so now what happens if you do symmetric difference? If you do symmetric difference, what happens is you will you have to, I will give you a small idea from this. So I'll recall this to here as a copy. Then I want to delete what we have just seen. So right, like that. Okay, so you try to delete what is here. So this is what you get, right? Alpha symmetric difference F. So here, so you try to prove is the same thing happens for k. So here let's take k difference, yeah, k symmetry difference is some beta. Now let's see what happens in right H. Okay, so let's find out what is so what is beta first of all. So beta gives you, it is H K F. So beta gives you like this one, right? So this is beta, you see. Okay, now let's look at what is H delta F. So H delta F is H delta beta, it is H union beta minus H intersection beta. So let's draw H union beta. So H union beta, let's try it. So you have already this fellow, that is K delta F, then you union with H, right? So you get all of this, right? Because this is your H K and F. Now what is H intersection beta? So H intersection beta, you can say right. So H intersection beta. So what that is this portion only, right? Now you try to define H symmetric difference of beta. You can see you are deleting these things from that, so you end up with what is called like this, right? and there is a fellow inside. Okay. So you can see that they are similar. So you can see alpha delta f is equal to h beta, or simply you can see h h delta k delta f is equal to h delta k delta f, right. So it is associative. So this becomes a group, right. So so these are the examples. Now if you go for some non examples, I will quickly recap the non examples. So what do you mean by a non examples? So non example of groups. So you need 4 conditions, right. So G star is not a group if at least one of the 4 conditions fails. So let us see some examples. So if you look at R in the usual multiplication, so here 0 inverse does not exist, being 0 is an element of R, so it will not be a group. Second thing, if you take all numbers like under addition, problem is identity is there, associativity is there, everything is there. The problem is inverse does not exist. If 2 plus minus 2 equal to 0, but minus 2 is not in whole numbers. Whole number starts from it is 0, 1, 2, 3 like that. So minus 2 is not there. So that is not a group. Second thing, as I have mentioned, is M matrices, n by n matrix with multiplication. So inverse does not exist for everybody. If you choose a matrix with the determinant 0, so this is an element of M2R, but because the determinant of this fellow is 0, its inverse does not exist, so it cannot be a group. So several things you can make like that. Okay. So next class we try to understand how finite groups can be constructed, right. Thank you.